Hi everyone, thank you for attending to this webinar. Previously, a colleague of mine made two presentations regarding time travel analysis. There were two different targets. The first one was on Windows 10, and the purpose was to analyze a vulnerability by means of TTA. And the second one was for analyzing an IoT object, which was a Wi-Fi router branded by Tenda. And in the meantime, I wrote a blog post to start talking about how we can also perform TTA on the Android platform. So today, I would like to illustrate what I've been talking about with actual demos. And the idea is not to present a specific vulnerability. It is rather for showing what it takes to record an execution trace that can then be analyzed by means of a tool that enables TTA. So I would like to start with showing you right away the tool that we use to view an execution trace. And then after, I'm going to explain how do we produce this kind of trace. So here we are on our platform. We run our trace viewer. So in this user interface, as you can see, you have different elements. You have the call tree. You have the assembly code that you can see in the middle. On the top right, you have the CPU context. Then in the middle, you have the frame buffer that we have recorded, and also the list of strings. You have in the bottom part, you have a timeline where you can navigate backwards or forwards in time. And you have some basic features for searching inside your trace. So in this use case, I'm going to show you, it's about the target was Telegram. And then I'm going to explain you how do we produce this kind of trace where everything has been recorded from the kernel space to the userland. So I would like to make a very short introduction first to time travel analysis for those who might not know what it is. So TTA is a debugging technique, but unlike an actual debugger, it allows you to rewind and fast forward in time through a program's recorded execution. So there are two steps involved. First, we have to record the execution trace. Then we have to analyze the execution trace in a dedicated tool like the one I've just shown you. So the same way as a debugger, it allows you to inspect the state of the program at any point in time. In the context of Android, there are so many processes running at the same time, asynchronous callbacks, JIT code generation, so many events going on. And as each run will never produce the same ordering, traditional breakpoints will require multiple reruns to analyze those events or any non-deterministic execution path. And with TTA, you have one recording and you can navigate through a timeline, and this even across processes and language boundaries. Because as you know, on Android, you can develop your application in Java or Kotlin and also in native. Regarding time slicing, you can treat the recorded program like a movie. You can pause at any specific frame, so you slice the single timeline wherever you want. Then you can look around that instant across the interpreted Java code or native libraries and so on. So therefore, TTA is really powerful as it turns any how on earth did we get here into an actual straight line investigating. So during this webinar, I'm going to make a short introduction about two different code tracing techniques. The first one is full system emulation and tracing. To put it in a simple way, we have created an Android emulator. We run a target application or any other process that we are interested in. We record the execution, and then any instruction that is executed is recorded along with all the memory being accessed. Then we generate an execution trace that can then be processed by a tool that provides TTA capabilities. So just to make it clear, we record almost everything. So it is very useful if the main question that you have is, how does a specific program interact with its environment? But sometimes you just don't care about that interaction. You just want to focus on one single process. So luckily, there are other ways to trace the execution of a program. All that we need is to plug our trace generator into the tracer to enable a more, I would say, lightweight TTA. In the previous webinar, Chilin was leveraged as the tracer. Chilin enables code emulation, but it is more than an emulator. It provides dynamic code instrumentation. It provides a whole analysis framework that you can use to analyze a binary by leveraging its code emulation capabilities. So we leveraged, in this case, we leveraged Chilin to trace the execution of a given binary, and we fed our trace generator with the necessary data to create an execution trace. In our case, we can use Frida for tracing the code. And once again, we are going to plug our trace generator into it. So if you don't know, Frida is a great dynamic instrumentation toolkit that provides a tracer engine called the Stalker. So there was already a similar project that exists, which is called Freenet by the Synactive team. Well, the objective is to leverage Frida to generate a trace that is compatible with IDE plugin called TNet. The idea is the same, but we want a trace that is compatible with our TTA tool. So now let's talk about the use cases I'm going to present. To illustrate how we record the execution of an Android application and to enable time travel analysis, we are going to use Telegram as the target application. The first use case is a discussion between two users through a secret chat. In Telegram, you have two types of chats, cloud-based chats and secret chats. So for regular private and group chats, data are encrypted between the server and the client, and for secret chats, it is end-to-end encrypted between two users. That was for the first case. The second use case is a regular chat between two users where a sticker is sent. So a sticker is just a static or animated image. And the third scenario is again a regular chat, but where a file is sent as an attachment. For the first use case, we are going to leverage the full system emulation. There is no particular reason here. I just want to show you in the current context what it takes to have the final execution trace that I've shown you at the very beginning that we can analyze later. The second and third use case will leverage Frida instead. So to illustrate the cases when we do not want to record the whole runtime environment, but just our process. We are then going to set up our testbed to make sure that we have all the prerequisites fulfilled. For the first case, namely for a full system tracing, we need to create two Telegram accounts. Therefore, we need two phone numbers because to create your account, you need a phone number. We are going to use one physical device to send the message and our emulator for receiving the messages. The thing is that sometimes Telegram will require you to provide OTP codes that are sent to you. And on the emulator, there's no SIM cards or eSIM. So instead, we have a third device that comes with a SIM card or an eSIM that just aims at receiving the OTP codes. For the second and third case, we are going to need two actual devices and thus two phone numbers. One device must be root so that you can run Frida server, and that's it. We can now move on to the first demo. So just a quick summary of what you are going to see during this first demo. I'm going to create a project. I'm going to set up the ideal state of the Telegram. So this is one of the most important parts. We want to set up this ideal state because I want to start the recording from a very specific state so that I don't have to record everything. Like I don't want to record Android booting. I don't want to record the app installation. I don't want to record all of that. I just want the application to be already ready to start the recording. So we want Telegram to be already running. We want the user to be logged in, and we want a secret chat already created and the two users ready to communicate between each other. Then I'm going to save this state and I'm going to start the recording from this specific state. So here we are on our platform esReverse, where you can record, launch an emulator, start the recording, and then generate the trace and view the trace in our dedicated tool. For this demo, if you remember, I want to record the moment when a user receives a message through a secret chat. I don't want to record Android booting, as I said, and so on. Therefore, I need to set up everything so that I can start the recording at the right moment. So here I'm going to use, the very first step is I'm going to use a command line tool called Start Android. I'm showing you the helper here, the help menu. So we are going to prepare the device and the applications. And what I mean by that is that I want to set up the device and the application so that we are in a state from where I can start recording the execution of the application. So Start Android here is the tool that we use to manage our modified Android emulator. We have just shown here the different images, Android images that we can manage for now. The first one is Android 12, but without the Google services, and the second one with Google services. We are going to leverage the second image here because I already know that Telegram requires an Android image with the Google services enabled. So we are going to create a project where this image will be copied to. And once that's done, we are going to see a directory named disks that has been created, and it contains our disk image. We are now going to launch Android by pointing the emulator to the disks we have already created. And by default, the emulator only uses a single CPU core, which makes everything sluggish. But since my immediate goal is simply to install the application, log the user in, this single core setup would slow us down unnecessarily. But the good news is that because all the write operations are preserved on our disks, so we can safely restart the emulator at any point without losing our progress. So to speed things up, I'll start the emulator in a multi-core mode, which we are in right now, and we are going to install the application and log the user in. So once that's done, we will have our application running and our session preserved, ready for the next steps. So as you can see, I've used ADB to run the application using the package name and the main activity name. If you don't know where are those, you can just go open the application, the APK inside tools like JDX or APK tool to view the manifest file and pick the package name and the activity name from there. Then with ADB, we run the application. Up. So as you can see here, Telegram, we have already logged our user in. We have already created a secret chat between a user called John Doe and our user is named Jendo. I just omitted the detailed login sequence here after installing the application. Basically, you just launch the application, you enter a phone number, you receive a one-time SMS code, you enter that code, and then the user is authenticated. Now my disks are ready. My application has been installed. Anything that has been written on the disks and that are meant to be persistent will survive to the next run. So now I can quit the emulator. But we're not quite ready yet to start the recording. First, what we need is to create also before starting the recording, we need to capture only the moment when a message is received. To do that, we'll restart the emulator, launch the application, and then navigate back into the secret chat. With the secret chat open, we'll take a snapshot so our recording can begin from that exact state. So we skipped snapshotting during the first run. If you remember, I made the first run in multi-core mode. We did not do the snapshot at that time because our recorder only works in single core mode. So for this first step, we have run the emulator in single. For this step, actually, the current one, we are going to run the emulator in a single core mode so that the recording can work. So once our Android has booted, we are going to start the application the same way as we did earlier. Then we are going to open the secret chat, and then that's it. We will need to save this exact specific state now. So here I'm launching Telegram. It starts. We have our secret chat. We get into it. So now this is the state that I want to save because I want the recording to start from here. So I'm going to save a snapshot for this. So I'm going to use Netcat to connect to the emulator and use the command save VM. And I'm going to name the snapshot Telegram secret chat ready. And that's it for this step. Now we are ready to start the recording. We are going to run the emulator in recording mode now. So as soon as the application appears, it means that the recording has started. Then I'm going to use another device to send a message through the secret chat. So here I've connected to my device, computer, a second device, a real device this time. I'm just screen mirroring the device here, just to show you that I'm going to send a message from this device. So we are going to use this device to send a message. Then as soon as the message is received, I'm going to stop the recording. So I'm starting the emulator now. So right now the recording has started, and I'm going to send the message. So here, as you can notice, we have a black screen on the device on the right. So this is because in a secret chat, the Telegram application prevents anyone to record the screen or to take a screenshot. So we already took care of that inconvenience in our emulator. So that's why the screen is not black. So I'm going to type the message. So as soon as the message, which is hello, as soon as this message has been received by the other user, we are going to stop the recording by just quitting the emulator. So the message is received, and I'm quitting the emulator. So now the recording is finished. So just to throw some numbers related to the recording of that use case, in terms of Disk space, the snapshot takes 13 gigabytes. The trace in total is about 323 gigabytes. So that's the trace that I've shown you at the very beginning, but that we will see later on in the presentation. And to set up everything, starting the emulator, setting the other device, installing Telegram, and so on, it took about 45 minutes. The actual recording takes about 5 minutes, and the trace generation took more than 21 hours. We had to deal with 7 billions of recorded instructions. So that's quite huge, because remember, we record everything from the kernel space to the username. So now let's move on to the second demo, because here we have previously we have recorded in a full system emulation context. Now we are in the case where we don't want to record everything. We are just interested in recording Telegram. So for this second use case, instead of doing a full system recording, we are going to have a more straightforward approach. And in this case, we are going to use Frida Stalker to trace the execution of only the application. In the previous use case, the beginning of the recording was as soon as the emulator starts in the record mode. That's why we have saved a snapshot so that when the emulator starts, it does so in a specific state. The recording then starts from that state. Now, in the context of Frida, the beginning of the tracing will be whenever we want it to start. And by whenever, I mean as soon as a specific function or entry point of our choice is executed. But then the question is, from where do we actually start? What function to target? In our case, we took two approaches. We read the source code and the documentation because luckily it is available. And we leveraged the tool Frida Trace to trace and track when a given function is being called to identify who is calling who. By reading the documentation, we learned that the message payloads and files that are sent, they are delivered via MT-Proto, which is the encryption protocol used by Telegram. Also, we have noticed that AES is heavily leveraged for encrypting or decrypting payloads. So based on this information, what I'm going to do is I'm going to send a sticker to the user, and I'm going to use Frida Trace to monitor this operation. More specifically, I'm going to trace any function that has AES in its symbol name. This way, Frida is going to track all those functions. And what you can notice here is that when I send the sticker, a specific function named AES-IGE encryption is called. Then once I know that this function is called, I'm going to create a custom script to tell Frida to generate a backtrace to know exactly what is the list of functions that have been called and that led to the call to our function. As we have the backtrace, we are going to read the documentation and the source code related to those functions to know their purpose. Among those functions, two are of particular interest. We have onReceive data, which is called to reassemble a full MT-Proto packet. Then we have onConnection data received that kicks in, which is responsible for handling MT-Proto packet. Namely, it is responsible for decrypting, deserializing all possible objects managed by Telegram. So we have two different very interesting entry points here. I know for sure that both will be called every time Telegram receives some new data from the network. So both are already good candidates. However, I'm already aware of what it costs in terms of disk space and processing time it will take. So depending on how much operations I want to be record, I'm going to choose the proper entry point from where the recording will start. So in my case, I arbitrarily chose to target on connection data received because at that time, I will already have a complete empty proto packet. And for now, I'm not interested in what's happening before. So what I'm going to do is to write a Frida script to intercept the function on connection data received. Once it is intercepted, there is a specific function called trace that will be triggered to start the recording. That specific trace function leverages the Frida stalker to trace the execution of the application. And it will monitor all memory accesses and dump the memory sections that are involved along with the CPU context. We have also defined a whitelist that represents the modules that we really want to be included in our trace. And we have also a blacklist of the memory sections that we don't want. In the modules that we want to be included in our trace, we have our native shared library, which is libtmessages.49.so. We also have the Android runtime library to catch all the interaction between the Java code and the native code. We have the libc library, the linker, and we have the art runtime library because it is the actual runtime engine that executes the application's Java or Kotlin code. So we are also interested in recording that. So I'm now going to show the next demo. These are the different steps that are performed before being able to view our execution trace. We are going to set up two real devices, one for sending a message and then a second one that will receive it. Then I'm going to start the recording with Frida. And before being able to view the execution trace in our tool, we will need to create a partial copy of the same file system that is on the second device. This is because our tool uses the native libraries that are leveraged by the application to fetch extra information, like for instance, the symbol names. And finally, we can start the trace generation and then view the output in our tool. So let's go for the next demo. So first of all, what you see on the screen here, right below you have the two devices, two real devices. On the right, you have the device for sending a message and the second one on the left for receiving it. The second device runs the application that we are going to trace using Frida. And on the right here, I have a terminal from where I'm going to open a shell, a rooted shell on the second device so that I can run Frida server. There is another terminal above here from where I am going to run my Frida script. The browser on the left here is our platform on which I'm going to upload the trace so that I can view it. So first of all, here I'm showing again the Frida script that I'm going to leverage for instrumenting the Telegram application and trigger the tracing. So in the terminal here, I'm going to first run Frida server on the device on the left. And then on the top right here in the terminal, I'm going to run my Frida script. Then we are going to inject this Frida script in the application to hook the function named onConnectionDataReceived. And as soon as it is called, it will trigger the beginning of the tracing. So on the device on the right here, I'm going to select a sticker and I'm going to send it. And as you can see on the top right, the tracing has started. I'm going to speed up a bit this part where the different accessed memory sections are going to be dumped. So the device on the left here is about to receive the stickers. As you can see, it's a bit slow because we are tracing everything. So the tracing slows the application down. And as you can see, we are starting to dump the different memory sections that were accessed during this operation. We have received the sticker, we have dumped everything, so now the recording is finished. So now we can check what are the files that have been created. So we go inside the trace directory, and we have different files that have been created here. So the trace is made of those different files. One in particular that we need for the next step is the file called usermodules.json. It contains all the modules that are leveraged by the application. The next step is to get all those modules which are on the device. And we need to recreate a file system on my computer that will contain those modules. We will include that file system in our trace then after. When we open the JSON file, what you can see on the left, you'll see entries for every module on the device. We can use ADB in order to pull most of those files directly from the device, but some will remain protected, especially those stored in Telegram's private directory, which require elevated privileges. Modules that are under the system or vendor directories, however, can be extracted without issue. So without that JSON file, you'll notice two critical Telegram-specific files: the base odex file that we want to get, and also the libc messages native library. So we are going to get all those files. So on the terminal on the top here, I'm inside a rooted shell. I'm going to move the base odex file and the native shared library in a directory that can be accessed by ADB, which is data/local_tmp. And then from those files, I'm going to change the owner of those files so that ADB can pull them. We are not using ADB root here because we want an emulator that is we want to minimize the modification that we make on the emulator so that it is not that easy to detect that it is a modified version of Android. Then on the left here, I have a bash script that I'm going to use to use the ADB pull command to get all those modules. And then we're going to create a directory named user.lightfs where I'm going to pull all those modules. I'm going to copy the name of the shared library and also the name, the binary called baseodex. Here I've copied both of those files here because, as you might know, when you install an application, the directory name where the application is going to be installed is a randomly generated name like so. All of the files that are inside system and vendor will never change, but for the directory name particularly for the application will be randomly generated. So that's why those two files, the path for those two files have been copied inside the script. Then I'm going to start to execute the script and pull all those devices on my computer. Then we can use the tree command to see what's inside the user.lightfs directory. As you can see, we have all the files that have been pulled except the base.odex file and the native library that we have previously moved inside the directory named data/local_tmp. So now I just need to pull them from the device using ADB. and we are going to move them inside the proper directory inside our user lightfs directory. So now everything is ready. I can upload my trace on the esReverse platform. But there is actually one missing step. Right now, many symbols that are stripped inside my native library, which means that there is no function name. So in order to give a symbol name to all those functions, I'm going to use a script in IDEA to publicly export all the symbols inside my binary. So let's say I have renamed symbols inside IDEA. I've added some preliminary reverse engineering, and I've renamed the symbols. If I want them to be included inside my binary, I can rerun the script inside IDEA to patch the binary to export those symbols, to make them available so it is easier in our TTA tool to spot what function it is, instead of having offsets. So these scripts work for IDEA, Binary Ninja, and Ghidra, by the way, but for this demo, I'm just using IDEA. So now that my binary is patched, I can move it into my file system. And I'm going to move it into the user lightfs directory. So now that my binary is patched, I can move it into the file system, and we can now open the trace in our graphical user interface to start doing our time travel analysis. So the interface starts. I'm not going to do a full analysis, just to showcase you what you can see. So as I showed at the very beginning, on the left you have the call tree, in the middle the assembly code, on the right the CPU context, the string list. You have the timeline in the bottom here, where you can click and navigate through the trace. So, and basic search functions here. So if you remember, we only recorded the Telegram. So we have only the Telegram process here, and not all the not the kernel space or any other process. For the further use case, I'm not going to run everything because it is exactly the same thing. No script has changed. The process is exactly the same. Only the scenario has changed. I'm just going to select a file, a JPEG file that I'm going to send, and that's the scenario that I'm recording here. So as I said, it's pretty much the same, so I'm not going to spend too much time on that. So again, just to throw some numbers, just to compare the differences between the three different use cases. The generated trace for the use case number 2 and number 3 are around 2.5 and 2.7 gigabytes, which is way smaller than the use case number 1. It also takes less time to set up and record, and the trace generation is also unmatchable. But we only have recorded our process here. So in terms of number of instructions, as you can see, it's also obviously smaller compared to the full system trace. But okay, now we have traces. I'm going to finish with a very quick tour of the tool that allows you to navigate through the trace, because that I've started at the very beginning, but this time I'm going to spend a little bit more time to show you exactly, now that you have the traces, what you can do. So again, I'm not going to explain a specific vulnerability. It's just to give you a quick tour on how to use the tool. So we come back again inside our platform. We are inside the use case where two users communicate through a user secret chat. So that's what we have recorded here. We are going to open our graphical user interface. So what we need to do first is to identify in our timeline here in the bottom where we should focus. So to do that, we have different approach. We can have different approach. It really depends on what you have as information at the very beginning. But now the only information that I have is that we have a function called onConnection data received that is always called when a message has been received. So let's search for the symbol onConnection data received. So we know that is inside the native library libT message, and the symbol name is onConnection data received. So we are going to search for that symbol. So as you can see, there are 6 different results that you can see in the timeline here, and I'm going to zoom in that location just to see that we have actually 6 different results. So now let's navigate at almost the very end of the timeline up. If you remember, the message that we sent to John Doe was hello, that you can see in the from buffer here. Now the question is from where do we start? It really depends on what you are going to try to reverse engineer, and also the level of information that you already know. As I already showed you, you can already search for the symbol usage, but you can also start by analyzing the code from where the function onConnection data received is called. And as it is called 6 times, I need to know which one is related to the receiving of the message hello. So instead, I'm going to search for the string hello, because that's the message we received, and we want to know if it is possible to go back in time to manually track our message. So I'm going to search for the string hello here, and we are going to select the very first hello. Then we are going to look at we're going to double click and look at the memory access history right below. You can notice who is using the string, what type of memory access it is it read or write, and at what transition it is located at. So transition, it is just at what offset it is located at. Remember the area we are interested here, that we are interested in is the area here. The red line that you can see here at the very end of the timeline is the location where we are at right now. Now pay attention to at the blue line that is going to appear, that is going to change location when I'm going to put my mouse over different strings. So the first string shows a yellow blue line that is before the area of interest, and the second one shows a blue line that is right into the area of interest. So let's select that string, and we can see that these are there are 3 memory accesses there. 2 of them are performed by a memcopy from libc.so. And let's select the first one, which is the earliest one. We can see in the right after we have clicked on memcopy, we jump into the code. We can see the assembly code that we have the instruction LDRW6 X1. And here X1 contains the string hello with the null terminal byte. We are going to select x1. And then we're going to select the linear address that is contained inside x1. We can then see a view of the memory at that time. And there is a checkbox here in the bottom. We are going to select show access history of selection. And it will show the history of all the memory accesses related to that specific data in memory. So let's look at the read access right above the one we are right now. And let's look at the same time at the call tree that we have on the left here. We have double-clicked on the read access, and if you look at the call tree, there are different functions that are called. Some of them are related to the art runtime. And there is also one specific one that is related to SHA-512. For now, there is nothing interesting, so we move to the next memory access, which is a write access. And we end up into a function that is called sub_129F404. The only thing that the call tree here can provide us as information is that we are actually in the Java code right now. As you can see, functions related to the art interpreter. Other than that, from the call tree, we can also see that the function 129f is called, but it calls a function called 125C54588 and also 12B23F20, which is called by 125C588 right here. In the assembly code view, we can see that hold on a second. 12B is called, then we come back into 125C, then we get back into 12A0 right here. If you look closely, we can see that inside the function 12A0 here, there are a bunch of AES instructions that are called. So it looks like we are in a quite interesting location in the trace here. And before diving into the assembly code, let's gather more information to draw a better picture of where we are actually right now. So let's come back into the function 129F4 and let's jump at that location, and we are going to scroll a bit up into the assembly code. And you'll notice that the function 129F404 is called by the function Java or Telegram Messenger, blah, 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 AES IGE encryption. So for now, we can stop the analysis here. The objective here is not to do a full analysis, but it was just to show you that by leveraging basic search function, we can already start to navigate in time through the trace. By searching for symbols, we can identify in the timeline the area where they are used. By searching for strings, we can start navigating backwards in time through the memory. So we went back in time to locate where is the message decrypted, which gives me another starting point from where to continue the analysis. But this is for the next time because we are already out of time right now. And to wrap up this webinar, I would like to finish with the next steps. We have now 3 different execution traces that we have recorded. We have 1 full system execution trace and 2 single process execution trace. Besides doing reverse engineering, our next objective to try to identify vulnerabilities in the version of Telegram that we have recorded. We can use the lightweight single process execution trace to iterate fast on pure user-land logic bugs. And the moment you care about kernel races or cross-process media helpers or even interactions with the key store, for instance, being able to do a full system recording comes in handy. And as Telegram is still a popular messaging application, due to the fact that it has a huge user base, it is rich media focused, and even though the server logic is closed source, MT Proto is public, and all of these makes Telegram an attractive target to explore. So what we can look at next, first, everything from images and stickers to audio and video, Telegram relies on a variety of third-party media libraries to handle parsing, caching, compression, encoding, and decoding. Any one of these components could contain a memory safety bug that might be exploitable. So beyond media helpers, the MT Proto packet format itself presents another rich target because structure-aware fuzzers have long been used against MT Proto to uncover subtle flaws or unexpected behaviors that attackers could abuse. We should also consider the privacy of secret chats. Like, is there any way an attacker could leak encrypted messages or sneak a malicious file past the client's defenses? Finally, even if someone manages to execute code on the device, we need to ask whether they can break out the Telegram sandbox. So all of these avenues, from media parsing to protocol handling to sandbox boundaries, offer promising opportunities for discovery. And that's a wrap. That concludes our session. I hope this webinar has clarified the steps involved in recording an Android application execution using Telegram as our example, and shown that how you can capture an execution trace. You also had a brief look at how you can navigate through the trace in time with our tool. And in our next session, we will dive deeper into the analysis phase. So if you have any questions, please don't hesitate to ask in the chat, and I'll be glad to answer them.